Okay, in the alkene we have one sigma bond and one pi bond, but in the alkyne I wanted to explicitly say that we have one sigma bond and two pi bonds. So which one of these is going to require the greatest amount of energy to separate the two carbons? The alkyne, right? But which one's going to be the most reactive? I need a bold answer. Somebody shout it out. The alkene? I'm getting votes for absolutely everything. What makes something reactive?
Its ability to...
Okay, all the reactivity that's going to be discussed in this course, like I said earlier, is based upon electrons, right? The valence electrons. Okay, we said that the alkene was going to be more reactive than the alkane because it had the pi bond. Okay, in other words, the electrons were more available for attack. How about the alkyne?
It's got two pi bonds, so it'd be even more.
Correct. Okay, the alkyne is typically going to be more reactive than the alkene. All right. When naming alkenes, we follow a lot of the same principles that we follow for naming alkanes. There's just one big difference. Okay? In this case, we have a double bond present and we need to be able to account for it in the name. So our first step here is to find the longest chain. Okay, but it has to be the longest chain including the alkene. I'm sorry, I should say including the double bond. Okay, what does that mean exactly? That means that I can have a chain of carbons that is 25 carbons long. But if it branches at one point and has one carbon then an alkene, it has to follow that pathway. So let's look at an example kind of like that. What's our longest chain here? Okay. 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Okay. Sometimes people are tempted to use just that bottom chain there and then treat the alkene as the substituent, but that's not the way it should be done. All right, so there's 10 carbons here. The next step is to number giving the double bond the lowest possible number. In other words, you want a number from the end that is closest to the double bond. Okay, so in this case right here, we say there's 10 carbons. What's the prefix for 10? Deca. And is this an alkane or alkyne? Alkenes. So what's the parent chain here, you think? Dekene. Okay. But I'm sure you can all imagine that there are probably several different isomers with the double bond in different positions in dekene, right? So we need to indicate where the double bond is. So where do we count from? So 1, 2, 3, 4, 5, 6, 7, 8, 9. We're never going to use these numbers here. Okay. The way we indicate where the double bond is by putting the lowest number of carbon that is part of the double bond. Does that make sense? This double bond is between carbons 1 and 2, so we indicate that it's a 1 dekene. Now, what do I have to put between every, what? Dash. Okay, am I done?
No.
What am I missing, folks? Okay, we have to identify substituents. Okay, in this case, the only substituent that we have is the methyl group. And which carbon is that on?
3.
Okay, that is on carbon 3. So this is a 3-methyl-1 dekene. So let's try a couple examples here. How would you name this? I know it's cruel and it's evil. But we start the same way we start anything else. Okay, by the way, there's a hydrogen there. I don't need to put that there, but I will for now. What's the first thing I do? Find the longest chain. So let's go here. We'll see 1, 2, 3, 4, 5, 6, 7. Agreed? Okay. Which end do we count from?
So from the right side.
From the right side. But the bromine's on closest to the left side. That's the first branch point.
Yeah, but the double bond takes precedence.
That's the word I'm looking for. As we proceed through here, we're going to be introducing new functional groups that are going to take precedent over others. Okay, so an alkene takes precedence, the rules for an alkene takes precedence over the rules of an alkyne. So in other words, the alkene overrules the bromine. Okay, so good. Was that the word they used in the book?
I don't know.
Well, okay. Playing it cool, I see.
This is just the big one.
All right, so we start counting from the right side with 1, 2, 3, 4, 5, 6, 7. Okay. What do I do now?
You put the number of the heptene. It's 7, so it's hep, and it's an alkene, so it'd be an E, so it'd be heptene.
All right, so we have a heptene.
Which is on the 4 bond, so it'd be
What do y'all think of that? Right, it should be the lowest possible number, so it's 3. So it's 3-heptene, very good. Now what do I have to do? Got to identify the substituents. So my substituents here are bromine. What's this feller here? It's an ethyl group, right? Okay. So what carbon is bromine on? And what carbon is the ethyl on? Now, how do I do this? Okay, it has to be alphabetical. I'm not going to say 3-ethyl, 6-bromo, because we have to follow alphabetical order. So that means that we go 6-bromo, 3-ethyl, 3-heptene. It's a little bit snug there. As you can see, I've been doing this for years and I still can't estimate the amount of space that I should leave for those prefixes. So if you find yourselves having to rewrite the answer, just rewrite it. Okay. Now I'm going to show you an interesting example here. One that's going to throw a monkey wrench in the whole darn thing. What's this? I'll draw the CH2 here, but I don't really need to. It's assumed. I'm waiting for a complete correct answer.
1-butene.
1-butene. Okay. Okay, 2-butene. How about this? Okay, this is also 2-butene. Unfortunately, we have an issue here. Okay, the whole point of IUPAC was to make sure that every single molecule or every single compound had its own unique name. These two are different. I'm sure several of you can already see that they're aligned a little differently. If I were to treat the double bond as a wall, on one molecule, the CH3s are on opposite sides of the wall, and on the other molecule, they're on the same side of the wall. Now, I know some of you might be thinking, it probably rotates in between the two, right? We can have rotation about single bonds. Why not have rotation about double bonds?
Because they're too strong.
Well, think about it like this. Take your two fingers, put them together, okay, and make them rotate as much as you possibly can like this. Now put a second finger there and see how far you can get. What happens if I try to twist?
You get a shorter rotation.
Well, I can only get flexing in either direction. There's no way for me to get this to rotate completely 180 degrees. The moment I try to leave that perfect alignment of p orbital overlap with a pi bond between them, the moment I try to twist, I'm breaking that bond, and that requires an immense amount of energy. I'm not saying it's impossible. I've personally had to do it for some of the projects I've done in the past, but you have to irradiate it with high energy UV light or add some kind of a high energy reagent to make it break that double bond. So as it sits in the bottle, those are two distinct chemicals, each with its own set of properties, different boiling points, okay, different flammabilities, different spectra, which we'll talk about that a little bit later. So when we have a situation where we have two groups that are on opposite sides of the double bond, in other words, on opposite sides of the wall, we use the prefix trans. Okay, and if they're on the same side of the wall, we call it cis. Now there should be a dash after the trans and the cis. And if I were to be a real stickler, I'd demand that you underline cis and trans because they're supposed to be italicized or underlined, but I'm not too worried about that. All right, so these are two distinct separate compounds with their own unique names.
So the trans go before the two?
Yeah, let me rewrite the name here. This would be cis dash 2 dash butene. Okay, and you can extrapolate what the other one would be. All right. Those are some simple examples. Let's try an alkyne. What would we call this?
1-butene.
Careful. Give everybody a minute to kind of look it over. This is much more complex than just a simple alkyne. We have a couple side orders of halogens. Okay, what's the first thing we need to do? Longest chain. So we have, I'm going to start from the end, obviously, that the alkyne starts at, because I'm sure you can imagine that it follows a similar rule to the alkenes. So 4 carbons. So as Carmen said earlier, it is a butene. And you're absolutely correct that it's a 1-butene because it's on the first carbon. What about the rest?
3 on both chloro and chloro.
But how's it supposed to be laid out?
3
chloro.
3 bromo, 3 chloro, 1 butene. Bless you. 3 bromo, 3 chloro, 1 butene. Now, do I have to worry about cis and trans here? How many different isomers can we possibly expect of an alkyne? It's just going to be the one. Okay, so we only have to worry about cis and trans when we're talking about the alkenes. Here's a fun one. All right, who's got an answer for me? Cyclohexene. Right, Greg. Okay, we just look at what it would be without the alkene. Now, do we need to put the 1 in there? In a cyclic system, we do not have to put the 1 in there. Because really, honestly, it couldn't be anywhere else. It's going to take precedent. No matter what else we put on that chain, it's going to be the number 1. All right, let's make this fun. What do we do in the case of where we have 2 double bonds? Well, we have 2 alkenes. So we say that this is a diene. So what we do here is we look at this and say, all right, our parent here is cyclohexane, but it has a diene in there. So we call this cyclohexa emphasize that diene. Now we need to indicate where the double bonds are. It doesn't matter which side we count from in this case. 1, 2, 3, 4. This is 1, 3 cyclohexadiene. Yes?
Why is the diene at the end? Like, does that just mean there's 2 of them?
It indicates there's 2 double bonds. Okay, what would you call this? It's close, but it can't be the same. 1,4. I'll give you that. It's a hexadiene, but you're forgetting the cyclohexadiene. Nope, we don't need to worry about cis and trans here. Potentially you could, but to have trans in a ring, you'd have to have a very large ring. So are we feeling comfortable with these naming schemes? If anybody does not, now's the time to say it.
Well, I just don't understand why it's 4. Because when you start at the beginning. Oh, okay. I was kind of like mine was.
You have, okay, so that's a good question.
And then
Why is it this? Why don't we count like this?
because we need to count the whole.
We have to count in a way that includes the double bonds. Yes. All right. Now, when it comes to alkenes and alkynes, we've already said that their geometry is different from alkanes. How so? What's the geometry of an alkene? Planar. Okay. It's planar. It's trigonal planar, right? Okay. It's a flat molecule. What is the geometry of an alkyne?
It's linear.
It's what?
An alkyne is linear.
Okay, an alkyne is linear, and an alkane is tetrahedral. Good. All right, so remember the geometries. Okay, it's going to help you when you try to rationalize what's happening in some of these problems. What's going to have the shortest bond length of all 3? Alkynes, good. Okay, which one's going to be the most reactive? Which one's going to be soluble in water? Now remember, we have water, right? Imagine this. You got an aquarium full of water. Pure water. Okay, so one water molecule sitting there with its OH bonds, and another one sitting with its OH bonds, and the O kind of arranges itself next to the H of the next molecule, and they kind of arrange themselves with this system of hydrogen bonding. Water's happy. Okay, water's also polar. Now, I go and I take some crude oil, and I just dump it in there. At first, you might see it disperse throughout the water, but what's going to happen over time? Right, it's going to separate out and rise to the top. The reason for that being, and we talked about this a little bit last class, is that the water molecules, when they see the oil come in there, it knows that it can't hydrogen bond to it. The water is going to struggle to try to bond to other water molecules to get those hydrogen bonds back. And in the process of doing so, they're slowly going to collapse on one another until they push that oil either up or down. If the oil happens to be less dense than water, it's going to be pushed as a layer on the top. If it's more dense than water, it's going to be pushed down to the bottom. Okay, if you look at what happened in the Gulf Coast, they had two problems. They had a whole bunch of surface oil, but they also had a bunch of really, really heavy oils, more dense materials that actually fell to the bottom of the sea. Okay. An alkene is going to be slightly more polar than an alkane. Slightly. And an alkyne, slightly more than that. Not to the point that I would be comfortable trying to assign a dipole by any means. Okay? But enough to increase the van der Waals interactions enough that you would expect alkenes and alkynes to have slightly higher melting points and boiling points than alkanes of the same number of carbons. Okay, alkenes and alkynes are slightly more polar, again, not able to form hydrogen bonds, so they're not going to mix with water. So alkanes, alkenes, alkynes, they all are immiscible with water. Okay? They all have very weak intermolecular forces holding them together. Therefore, small molecules are expected to be gases, and as they get bigger and bigger, you increase the possibility of van der Waals interactions, and therefore increase the melting points and the boiling points. We also said that alkenes and alkynes are more reactive than alkanes. Can somebody remind me real quick, what were the two reactions of alkanes that we discussed? Combustion followed by halogenation. Okay, the reaction of methane I showed you with chlorine gas in the presence of light as an initiator. Okay, both of those reactions are relatively uncontrolled. Okay. It's Thunderdome inside of those reaction flasks there, okay? There's constant reaction taking place. You can't control the distribution of products, okay? Neither one of those are especially useful for the products they produce. Now, the alkenes, having their pi orbitals, and pi bonds, I should say, are much more amenable to reaction than their alkane counterparts. So let's say, well, you know what, I'm going to simplify this even further. And say, let's call this reactions of alkenes. And just know that just about every reaction of an alkene is applicable to an alkyne. Okay, all the reactions that we're going to talk about here today, and probably most of next class, are going to be addition reactions. Okay, and they all involve the breaking of the pi bond. Okay, you're going to see a lot of reactions. Okay, probably 5 or 6 different reactions. And that means that when you consider all the R groups that you could attach to the alkenes, by the time you're done with this section of the class, you should know about a million and a half different potential reactions that could take place. I know that sounds scary, but it comes down to really 5 or 6 reactions. Okay, so don't allow yourself to be overwhelmed, and please do not at any point try to memorize an individual reaction. It's not going to help you. Try to understand the type of reaction. And in this case, we're looking at additions. In an addition reaction, we have an alkene and I'm going to put R groups on here. What do those R groups mean? Functional groups, alkyl groups usually. But we're just going to call them our wild cards. Okay, they can be just about anything we decide to put there. Okay, and you're going to see that I use a lot of generic reagents when I'm trying to explain a reaction in general. In this case, I'm going to talk about reagent XY. Okay, I know that there are no X or Y elements on the periodic table. Okay, these are not intended to mean specific elements, but just a type of compound where you do have, it's a binary compound. And during the course of the reaction, the pi bond is broken and 2 new sigma bonds are formed. Okay, we call it an addition reaction because we are adding that molecule across the double bond. Now I know it's kind of hard to put this into context by looking at a general compound like XY, so let's try looking at something a little bit more specific. Let's say I decide I'm going to take ethene okay, and my choice for XY in this case would be chlorine gas, Cl2. We would expect the chlorine to add across the double bond. See, in this case, the X and the Y were the same thing. Okay, so what do you think would happen if we used bromine instead of chlorine? What do we make? Wow. You think about that one. If I took ethene and reacted it with, instead of chlorine gas, what if I reacted it with hydrochloric acid? Okay, I'm going to tag this H for the hydrochloric acid. Okay, what I would expect to wind up with is a product where H was added to one side and the Cl was added to the other side. Again, note the breaking of the pi bond. Let's try something a little bit more complicated. Not by much. What if I reacted an alkene with water? Now water doesn't seem to fit into that pattern there, does it? Well, make it fit. How do I make water into a kind of a, what's the word I'm looking for? How do I basically break water up into two distinct parts that could add across the double bond? H and OH. So H-OH. Again, I'll tag this H here. What you wind up with is a really, really inefficient way of making alcohol. Okay, but it's an addition reaction.